Hi, Rocco. Good morning, everyone. Okay, as usual, questions on chat. Any questions from the homework? Aiden, number 7. Okay, and which section, Aiden? I think I assigned from 2 sections. 6.6. All right. Okay, so we're gonna do 6.6. And we are going to be doing number 7 and 18. So we start number 7. Okay, let me look at it. All right. The problem is computing the surface area. Yesterday we saw the formula for the surface area is the integral from a to b 2 pi f of x times the square root of 1 plus the derivative square dx.
What is that?
Okay. So we look at number 7. We have the following. Find the area of the surface generated when the given curve is revolved about the x-axis. So we have y equal 3x plus 4 and x between 0 and 6. And we're going to rotate this about the x-axis and find the surface area. So let's draw a little bit the picture. 3x plus 4, that's a straight line starting at 4. So that's my line. And I'm rotating it about the x-axis. So it's just like yesterday's picture. What we're getting is basically a truncated cone. That's exactly a truncated cone, or what we called it yesterday, a frustum. And the question is, what's the area of this frustum? If you take it, open it up, what's the area of the resulting object? So we apply the formula verbatim here. First, I need to find the derivative. So usually I would recall this, I call this again f of x. The derivative is just 3. And now we plug in verbatim. So the surface would become integral from 0 to 6. That's my 6 in here. 2 pi times 3x plus 4 times the square root of 1 plus the derivative square. That's the derivative square dx. So this is equal to 2 pi is a constant. This is 1 plus 9. This is square root of 10. I can take this out. And I will be left with the integral from 0 to 6 of the quantity 3x plus 4 dx. And now the rest is relatively simple. Simple. Between 0 and 6. Antiderivative of 3x is 3 half x squared plus antiderivative of 4 is 4x. And then we will have 2 pi, the square root of 10 times. At the upper minus the lower. At the lower, it's a 0. At the upper, I will have 36. So I will have 3 half times 36 plus 4 times 6, which is going to give me 24. Equal, you guys do the math. Okay, and the unit is, end of the problem. All right. So I will look at number, what problem you guys have? Number 18. Okay, what's number 18 about? Okay, so we have y equal the square root of 5x minus x squared and x between 1 and 4. So we have a certain curve. Okay, so I don't know exactly how it looks like. If I plug in 1, I get 1 here. If I plug in 4, I will have 20. 20 minus 16, I will get a 4. So it's going to look something like this. So that's really the curve, okay? And the question is, so we're rotating it. We're generating a surface. This time, we're not generating a solid because we're talking about surface area. So we have to use the formula verbatim, which is I rewrite it again. That's the integral from 1 to 4 of 2 pi times the function times the square root of that quantity dx. As I told you, those integrals are made so that you can find them. So if you, we should be able to find those integrals. So I have to start by finding the derivative. So let me write my function again. That's 5x minus x squared. So first, differentiation. Okay, typical chain rule problem. It's a half. Whatever I have to the power a half minus 1 times the derivative of what's inside, which is 5 minus 2x. So this is equal to 5 minus 2x over 2 times the square root of 5x minus x squared. Now, back to the formula verbatim. So the surface area is integral from 1 to 4 of square root of 5x minus x squared times, so that's the 2 pi here, that's f of x, and this is the length of the little line segment. So it's 1 plus this quantity squared. Okay, so we try to do it slowly. It looks complicated, but as I said, if it's given to you, it means we should be able to handle it. Square root of 1 plus. Okay, let's take care of that. That's the quantity 5 minus 2x squared divided by 4 times 5x minus x squared. Okay? So, okay, what do you want me to do? I did something fairly similar yesterday to prepare you for those type of problems. What did we do yesterday? You guys remember? Anybody remember what we did? And you guys suggested what to do.
You could put it under a single square root and multiply it.
Exactly. That's what you guys said yesterday, and that's what I'm going to do today. So I'm going to take 5x minus x squared times 1 plus quantity 5 minus 2x squared divided by 4 times 5x minus x squared dx. Okay. So finally, if we do everything correct, let's see, this is going to be 2 pi times integral from 1 to 4 of the big square root. Remember, it has to work because those problems are made up. I multiply this by that, give me 5x minus x squared. Then I multiply this by this quantity. I will have 4 down here. And here I will have 5 minus 2x squared dx. Okay, so the last step looks really messy. We're going to find the common denominator and expand this term and hope for the best. Okay, the common denominator is going to be 4, that eventually I can take it out. I have to multiply this by 4, which leaves me with 20x minus 4x squared. And let's see what we get here. When I square this, I get 25 plus 4x squared minus 2 times 2, that's 4 times 5, 20x. And the magic is happening. I don't know how they found those problems. 20 minus 20 cancel each other out. Minus 4 plus 4 cancel each other out. Square root of 25 over 4 is 5 halves. So this will give me 2 pi into go from 1 to 4, 5 half dx. So finally, this would give me 2 and 2, so 5 pi times x evaluated between 1 and 4, because I took the constant out, and what I will be left inside is the dx. Antiderivative of the x is the x itself, and finally I will have 5 pi times 4 minus 1. I will get 15 pi. Okay, so it really looked complicated, but as I said, those problems are worked out so you guys can handle them correctly. All right, great. We still have number 13. You guys keep it for tomorrow. I would like to start the lecture today, and tomorrow, since it's going to be open for your questions, number 13, I will definitely cover it tomorrow. Are you with me? You guys just remember it, and I will cover it tomorrow. Okay, so today we are going to do the last piece before the exam, before our exam, and we are going to talk about work. Okay, so what is work? You guys, some of you had physics a little bit. Do you guys remember what is work? First, let us see. Work happens when you move an object. So if you take an object, whatever it is, and you move it, we say in physics that work has been done on the object. Intuitively, work shows how much change in energy happen when the object is moved. You know, when you take an object and you lift it, you give it more energy. Because when you let it drop it, it's going to do more damages than it is at a lower distance from the ground. So when you take an object and move it, you definitely, the object is gaining energy. And work is this physical quantity that tells you how much energy is changing when the object is being displaced. So anybody have a little bit remember what work is? What's the definition of work? It's force times distance, absolutely correct. So let's write this down and then we're going to work in it. So in physics, because we're definitely using the definition in physics. So in physics, I'll write it down. If a constant force, F, if a constant force, F, displaces an object, so the force causes the object to displaces an object, a distance d in the direction of the force. So it means if the force is up, we're assuming that the object is moving up. And in your other courses, you will take more general scenario. But this course only allows the scenario. In the direction of the force, then we say that work is done on the object. Is done on the object. And it is defined as follows. So in physics, we defined, and work is defined as follows. Okay, so if you have a constant force, which is moves an object, a distance g, then we say work is done on the object, and we define, as you guys said, that the work is the force times the distance. The more you lift it, the more energy you're giving the object. And the heavier is, of course, the more energy the object have. Okay, so very good. So unit of work. What's the unit? Okay, do you guys remember the unit? Exactly. Suppose the unit of force is Newton. It has to be Newton. And unit of distance is meter. Then the unit of work is Newton meter, if you want, which is called joule. Okay, so joule is the work you need to lift an object that the work done on an object that weighs, if you want, 1 Newton, if you move it 1 meter. Okay, that's the unit of work. So a very straightforward example before we move on. So for example, suppose so find the work needed. Work needed to lift a 3-kilogram book. A distance of, let us say, 4 meters. Okay, so if you have a book, which is, you're lifting it, a 3-kilogram, what's the work needed? All right, so let's find the work. The work is, so that's the constant force, which is the book. Force to lift, the force needed to lift. Times the distance. Okay, what's the force? The distance is easy, we're lifting it 4 meters. What's the force? Back to you, quickly. You have a book, the mass is 3 kilograms, and you lift it. What's the force you need to lift the book? I don't know where you got 12 joule from. I'm talking about force. Always listen to the question. My question is, what's the force you need? I did ask about the distance. What's the force you need to lift the book?
Isn't it mass times acceleration?
Exactly. It's the mass times acceleration. 100% correct. Remember, kilogram, that's a unit of mass. Okay, kilogram is a unit of mass. Exactly. So the force is going to be the mass, which is, mass times the acceleration. Because when you lift it, you're not fighting only the mass of the object, you're fighting gravity. So the force needed is going to be this times the acceleration. It means 3 times, and the acceleration is the acceleration due to gravity, which is 9.8. So the force is 3 times 9.8. That's the force. So the work is going to be the force, which is mass times acceleration. That's the force, times the distance, which is 4 meters. And of course, we do the math here. That's nothing. You get 147 joules. Okay, so we have to be very careful with unit. Kilogram is a unit of mass. If you want to become a unit of force, you'll have to multiply it by an acceleration. Otherwise, you're not taking the gravity into account, which is wrong because we fight the gravity as we lift an object. All right, so that's really a simple example. So if the force is constant, life is easy. Force times distance. But in this course, we don't let things be constant, we start varying them. So the question is how to make sense out of work if the object that we move it by changing the force we need to lift it. So question number 2 is variable force. Because if the force is constant, there is nothing else I can say. So variable force. So example of variable force. So I will give 2 examples. First example is, let's say you have a bucket and the bucket is full of sand. And there is a hole in the bucket. So as you're moving the bucket up, the sand is seeping out of the hole. Is the force to lift the bucket variable or constant in this scenario? Quickly. Okay, you lift the bucket, there is sand, there is a hole, the sand is leaking from the hole. So as you lift up the bucket, you lift up the bucket, what's going to happen? Is the force to lift the object going to be constant? Absolutely not, because the weight of the bucket is actually getting less and less. So the force is a variable force. That's an intuitive example of that. The example we're going to take today is a spring. So we're going to talk a little bit about a spring. Okay, so suppose we have a spring. That's a spring. And always, whenever we talk about a spring, 0, we're going to put a spring on an axis because we need formulas. And 0, that's the equilibrium position. So 0 is always put on the equilibrium position. Okay, and then we take the spring. So I draw another picture because I want to emphasize. So this is the spring. We take it and we stretch it. The question is, as we're stretching the spring, is the force needed to stretch the spring fixed, constant, or variable? Okay, so this is the spring. You're moving the spring. The force you need to move it, is it constant or variable? Very simple question, quickly.
It gets like tougher to move, so it would be a variable.
Absolutely. It's becoming harder and harder to move. But the more you stretch, the more force you need. The more you stretch, the more force you need. So the force to move the spring, so the spring was here, you're moving, you're displacing it. So you're giving it more energy, actually. You're giving it more and more energy as you're moving it. But the force is definitely changing. So how do we find the work in a scenario like that? That's really the idea. Okay, so before we find the work, I need to talk a little bit about the force done on a spring. So I'm gonna put here something probably, of course, you guys have seen before, Hooke's law. Hooke's law, it gives us an experimental law that gives us a formula for the force. That's what Hooke's law is about. What does Hooke's law tell us? So suppose we have a spring, that's its equilibrium position, and we stretch it a distance x. So x is the amount of stretching, not the length of the spring. I don't care about it. It's how much we stretch. And that's crucial. Amount of stretching. Okay, x is the amount of stretch. So I take the spring and I stretch it. So I imagine you have a mass here and you're moving it. And this is where, okay, I stretch it and I hold it. To be able to hold it, I need a force. Hooke's law gives us a formula for the force and tell me that the force here follow the following rule. It's always proportional to the amount of stretching. Proportional means that it's always a constant k times the amount of stretching. It's not a constant times x squared. It's a certain constant k times x. So let us write this down. So Hooke's law tells us the following. Okay. Whatever, I have it somewhere. Okay. So the force needed to keep a spring stretched, basically, or compressed by x unit beyond equilibrium because of the force needed. So you stretch it and you hold it. To be able to hold it, you need a force. X unit beyond equilibrium is given by, so that's the formula for the force. The force is a constant times x. X is, I repeat, X is amount of stretching. K is a constant called the spring constant. The stiffer the spring, the higher the value of K, called the spring constant. Okay, and this law is experimental. Isn't the force of the spring? No, no. It's a constant times X. It's proportional to the amount of stretching. Okay, it's proportional to the amount of stretching. You double the amount of stretching, you double the force. That's really what it is. So it's K times X. It's not X squared. All right, let us take a fairly simple example here. Okay. So let us say I tell you example. Okay. A force of 10 Newton is required to stretch a spring so you need to keep a my apology, it's required to keep a spring stretched 0.1 meter beyond equilibrium. Okay, so in my mind, what am I thinking of? I'm thinking of the following. This is my spring, that's the equilibrium position. We take it, we stretch it 0.1. So that's 0.1. We hold it here. And problem 10, to be able to hold it and keep it stretched at that much, you need 10 Newton. That's what's given to us. Question is, find a formula for the force. It means what's the force to move it? 0.2, 0.3. Find a formula for the force. Okay, so we give us one number that tell us if you stretch it 0.1, it's 10 Newton. The question is, okay, find it for anything, any other number. All right, the problem is easy because by Hooke's law, we're going to call f of x to be the name for the force. And Hooke's law tells me that the force is given by the formula K times the amount of stretching. And the question is, we need to find K. So to find the force, we have to find K because we know the formula once we can K. But what's given? What's given is that if X is 0.1, means the force, then this is equal to 10. That's what this is giving me. So this 10 Newton is the force when X is 0.1. So now we substitute. F at 0.1 is K times 0.1 is equal to 10. So this will give me that K is 10 divided by 0.1. 0.1 is 1/10. So it means this is equal 100. So the force is 100 times the amount of stretching. Okay, so if I know one value, I mean that's the the beauty of the formula. If I know the force to stretch it by one number, 0.1, I know the force to stretch it by any amount. So for example here, if I tell you what's the force needed to stretch it by 0.2 meter. So force to keep spring stretch. So the force to keep the spring stretched by 0.2 meter is F at 0.2. It means it's 100 times 0.2, which is going to be 1020 Newton. If I want to see how much we stretch it, 0.3, okay, 100 times 0.3. So now I know everything about the force. Okay. Now, work. So now we know the force. that we're working with, and now the work. The question number 2 is the following. Or problem number 2. So work done on a spring. So let's see what the problem is. So we are going to call f of x the force needed to keep a spring stretch x unit beyond equilibrium. X unit beyond equilibrium. Equilibrium. And the question is, find the work required to stretch the spring. To B units beyond equilibrium. Okay, so that's my problem. I have a spring, and I know the force because now we have the formula for the force with a little bit of information. Usually they either give you the force equal like 100x, or they give you what I did before. They give you enough information for you to find the formula for the force. So we don't have issue with the force anymore. Now the question is, what's the work we need to stretch the spring to be unit beyond equilibrium? Now the force is changing. So I don't have a force to work with. So there is no force times distance because it is changing. So what are we going to do? That's my spring here. And this is my equilibrium position. That's 0. 0 is always the equilibrium. And I want to stretch this to B unit. So I'm going to take it from here all the way to here. And you can imagine, think about energy. How much energy is going to change? A lot of energy is going to change for the spring. So how we are going to do it? Ideas? To the force, I don't have formula for it. I don't know what the force is. The force here is a number. The force here is different. The force here is different. The force is changing as I'm moving on. So what do you think we are going to do? What do we always do? Okay, cut up into little pieces, as if we have any other choice. We're going to cut up into little pieces and see what's the benefit of doing this. So I'm going to take this interval between 0 and B and cut it up into pieces. So I'm going to call this x1, x2, of course, x3, and I keep going. I call this, if you want, xi minus 1. So I can call this xi minus 1, and this is xi, and so on and so forth. Okay, so we're going to divide 0b, the interval 0b, into n pieces and subinterval. And delta x, which is supposed to be very, very small, is the length of every subinterval. It means the length, I'm not going to write what it is, the length of every subinterval. Every subinterval. Okay. All right, and now how are we going to think? We're going to think along the following line. Okay, I need to move this mass here. I'm going to stretch it all the way to here. Okay, the way we're going to think about work is like this. First, I'm going to move it from 0 to here. A little bit. I'm going to move it a little bit. And I'm going to find the work I need to move from 0 to x1. But here's the thing. The force is changing from 0 to x1. However, if delta x is very, very small, I can assume that the force I need to move it from here to here is not really changing a lot. Or I can assume that the force from here to here is constant. As long as delta x is very tiny, so it means if delta x is, let's say, 100, I can assume that to move it 100th of a unit, my force is constant. So on this little piece, so for delta x small, very small, we can assume that the force is constant. And what's the value of the force? You can pick anything in between. You can say that the force to move it from here to here is the same as the force to hold it fixed at x1 or at any point between 0 and x1. So we can assume that the force is constant and it is equal to the force at x1. You can pick anything. It doesn't really matter, but for the simplicity, I pick x1. So the work to go from here to here, so that's the work, is going to be the force times what? Times what? Back to you. If I move it this tiny bit, what's going to be the work? I'm assuming the force to move it from here to here is the same as the force at x1. But I have to multiply it by the distance. I moved it from here to here. What's the distance to go from here to here? You guys are not answering? Delta x. That's the delta x. So from here to here, I have delta x. From here to here, I have the delta x. So the way we're thinking about it is like this. I move it tiny bit and find how much work I needed. And I can do that because if delta x is small, I can assume that the force to go from here to here didn't change that much. Once I reach here, I said, okay, now I change. I said, okay, right now we acquired more force. So to go from x1 to x2, again, I will repeat myself here from x1 to x2, I assume that the force to keep it from here to here is the same as, is constant, is the same as the force at x2. And I find the work to go from here to here. So in general, I'm going to call Wi, we're going to call Wi to be the work needed to move, to stretch the spring from xi minus 1 to xi. So now I'm thinking, like we always do, a typical interval. So this interval from here to here. If I want to move it from here to here, the work that we call it usually Wi is going to be the force at xi, because you can hold it and move it. So you can assume that the force from here to here haven't changed. You can either use xi minus 1, you can use xi, you can use anything in between. We're assuming that all those forces are basically the same, times how much we're moving, which is the delta x. So let Wi be the work needed to stretch a spring from here to here. Then Wi is equal to the force at xi times the little delta x. Now, a lot of time in your physics course, they call Wi the element of force. Sorry, the element of work. Okay, so it's the work need to move the object tiny bit, because we can assume the force is constant during that time. So the total work going to be approximated by the sum of the work done on each subinterval. So it's the sum of work done on each subinterval. Okay. So it means we move it from here to here a little bit by assuming the force is not changing. When I hit here, I know that the force is changing. That's why I change. I use the force at x2 times delta x. All right, now I found the work from here to here. Again, now force is changing. I use the force at x3 as the constant value and multiplied by delta x. So that's how I am taking care of the fact that the force is changing. So this is going to be almost equal to the sum of the force at xi times the delta x, where my I goes from 1 all the way to n. And this is the Riemann sum that we're always after. That's the Riemann sum that we're always after. So the work is now equal to, so when n goes to infinity, it means when delta x become very, very small, the smaller the delta x, the better is our approximation, because we are making an assumption that the force is not changing on a subinterval. The smaller delta x, the better the approximation is done. So now we will have the work is going to become the integral from 0 to b of the force f of x times dx. So that's how the integral is coming up. So now we have the formula for the work. So now we have the following. Okay. The work done. In stretching, basically, or compressing. Or compressing. A spring from A unit to B units. So in the problem I gave you, I moved it from 0 to B, but actually if I move it from A to B, so if I move it from A to B, the logic is the same, but then we have to divide the interval from A to B. It's given by. The work is the integral from A to B of the force dx. And the logic is the only logic we can have because it's a complicated situation. My force is changing. What to do? We move a tiny bit at a time, tiny bit at a time, tiny bit at a time. The benefit is that if you move it a little bit, we can assume my force is constant. So we're taking care of the changes, but by dividing this into a lot of intervals. Okay. So now we're going to do two problems, I hope, about this problem. So problem number 1 is a very straightforward, direct problem. So problem number 1. Okay. So suppose I tell you that f of x is, I'm going to give you the formula for the force is 100x based on the previous problem I did. So question number 1 is find the work needed to stretch the spring from 0.1 meter to, let us say, 0.35 meter beyond equilibrium. Okay. So it's a situation where I gave you everything. There is nothing because we've already figured out 100x in the previous example. So the work is fairly simple. The integral from, so I'm going to stretch it. So that's my equilibrium. I'm going to stretch it from 0.1 all the way to 0.35, from here all the way to here. So to do that, we have to divide the integral from 0.1 to 0.34. So this is the integral from 0.1 to 0.35 of the force, 100x dx. And now we integrate this. 100 is a constant times the integral from 0.1 to 0.35 of x dx. So this is 100 times. Antiderivative is a half x squared between 0.1 and 0.35. And then the rest is simple math. 100 you can get it out, and then you will have 0.35 square minus 0.1 square, and you do all the math, and if I've done it correctly, you get that many joule. Okay, so that's a very standard problem. The force is given to you, then you have to find the work, and you just have to use the integral. Example number 2. Okay. So example number 2 is the following. I'm going to put it in front of you, and I want you to think a little bit before we proceed. So those are typical examples for work. Example number 2 is a work of 2 joule is required to stretch a spring 0.1 meter from equilibrium. So that's what's given to you. Question is, find work needed to stretch the spring 0.2 meter from equilibrium. Okay, so that's what's given to you, and that's what you have to find. All right. So what's the work to stretch the spring 0.2 from the equilibrium? And so let us see. The work is the integral from 0 to 0.2 of the force dx. Okay, that's what we have. So to be able to do this, I need the force, which is they did not really give me. They gave me info, a bunch of info, but they did not give me the force. So I'll give you a minute to tell me how I'm going to find the force.
Can you find the derivative of the work function?
The work is a number. The
Oh,
derivative is a constant.
okay. Wait, never mind. Hold on.
That's okay. All of you. Remember, I gave you information. Want all of you to pitch in. Luke gives me 20x. Luke, I will say you're right if you tell me how. I don't have a clue how you got the 20x. I don't think it's right. So f of x is, we know by Hooke's law, is k times x. F x equal k times x. So the question is, we need to find k. All right, to be able to work with the Grant gives me, okay, I'm going to write what Grant wrote, and I want you to criticize it before we move on. All right, because that's a typical mistake. Read what I gave you. A work of 2 joule is required. So is this equation correct? 2 equal k times 0.1. Can anybody criticize it? Exactly. That's what's given to you is work, not force. So this is Not correct because 2 is not the force, 2 is the work. Absolutely correct. So we have to use the fact that the work is 2 joule, not the force. Force, I gave it already an example. I'm not going to repeat the same example twice. Exactly. So that's the force, which is not given to you. 2 is work. So how are you going to set up the problem? What is 2? So that's what's given. 2 is the work. To stretch it 0.1. It means 2 is the integral from 0 to 0.1 of kx dx. So that's what we're given. And now we need to find k from that. I repeat, this is not correct because 2 is work, not force. If 2 were force, absolutely correct. So that's why I have to cancel this. The work is equal to 2. It means 2 is the integral from 0 to 0.1 of kx dx. And now we have to find the k. All right, I'm going to set the work equal to that. So this tells me that 2 equal k times the integral from 0 to 0.1 of x dx. And I need to find my k. So this will give me the following. 2 equal k times a half x squared evaluated between 0 and 0.1. It means 2 equal k over 2 times 0.1 square, because I have 0 down here. So this will give me that 0.1 square. 0.1 is 1/10. So it's give me 1 over 100. So this will give me 2 equal k over 200. It means my k is 400. Okay, so go over it and think through it. I'm giving you work, I'm not giving you force. So this will tell me that my force, f of x, is 400 times x. So that will give me the force. Now I need the work. So the work to stretch point 2. Now I can find it because I found my force. So work to stretch 0.2 is equal to integral from 0 to 0.2 of 400 x dx. 400 is a constant. I take it out, and I'll be left with a half x squared between 0 and 0.2. And this would give me 400 over 2 x squared squared 0.2 squared minus 0. And then I do the math, whatever it is, and I get, I think, 8 joule. And of the problem, right? So, you know, when you have a problem, you read it 2 or 3 times to, you know, to be able to figure out what's given to you and how to use what's given to find what you want. Right? So this will be the last idea we cover before the exam. You guys, please do the homework for tomorrow. And tomorrow will be open as usual. You ask any question you want about the review. All right, so you do the homework that I'm going to assign, and I will ask any question you have, including number 13 that I did not answer for today. All right, any question before I let you go?
Is your office hours right after this?
For today is from 2 to 3. But if you have
Oh, okay.
questions, I can make it. Yes, the lecture of today is absolutely. No, okay. The lecture of today is absolutely on your exam. I always give question that has to deal with spring, and they are usually shouldn't do well in those questions. So do your homework for tomorrow, and you will be okay with that. And Zoe is asking me, do you have to sign up for the testing? My understanding, you don't have to. You just show up. That's what I was told. So hopefully they are correct. They told me that they will sign you up. You don't have to. So you just show up. Okay, any other question? Okay, so today's lecture is on your exam. You do your homework for tomorrow and you will be all right with this section. It's not really hard because it's just basically it's just a formula that you should be able to work with it. Anything else? Okay, so office hours today are from 2 to 3, and please show up as well as tomorrow. Please show up.
Have a good one, Professor Elias.
You too. Bye-bye, guys. See you tomorrow.